radiation heat transfer. So why we are talking about radiation if, as I explained in the simplified fill rod diagram here, that we always having conduction and convection all the time. Let me get that diagram again. There you go. He said that we have conduction in the fuel pellets. Then we have conduction through the stagnant helium layer. Then we have conduction through the wall of the clad. Then we have convection outside. In reality, because of the fuel is at very high temperature, there is actually radiation going out between the fuel and the interface of that cladding. There is always radiation happening too, but we are not going into that in this course. So, but that's why I'm bringing radiation into the discussion, just to refresh your memory about it. So what is radiation? Radiation is transport of energy in a form of electromagnetic wave when you have a vacuum atmosphere. So transport of energy in electromagnetic waves, especially through vacuum. Sun rays are bringing energy from the space to the earth, and the energy is coming by radiation because it's going through a vacuum. There is no atmosphere outside the atmosphere layers, right? So that's what it is. And that's usually happening when you have a very high temperature, super hot surface. Usually energy goes by electromagnetic waves. So radiation is gonna be in the form of emitted energy to where? To the surrounding. This is called surrounding. Even if you have atmosphere here, if you have molecules, media, or a medium in the middle, you will have radiation because of that super hot temperature here, okay? So how to calculate the total energy emitted, Q, emitted by a surface, very high temperature surface to the outside. So imagine that you are bringing, you want to do a barbecue and you have a sheer coal and you burn it out, then you put your hand around the coal, it's emitting too much energy. So Q, which is the emitted energy, can be calculated from epsilon sigma A T surface to the fourth. And this is called Stephen-Boltzmann law. Stephen Boltzmann law. So Q emitted by radiation from a surface, it's calculated from epsilon sigma A, I will put the AS, TS. Excuse me. Let's define each one of these terms. So epsilon is called the emissivity, which is ability of surface to emit energy. And that's a factor that between 0 and 1. And this will be given to you based on the material, okay? Sigma has no units, so it's a factor. Then sigma is Boltzmann constant, Boltzmann constant. That's 5.67 times 10 to the minus 8 watts per meter square Kelvin to the fourth. Okay. Then AS, anybody will emit energy, will radiate energy from the surface. So A is actually the surface area. And this is in meters square. Then TS is the surface temperature. Number 1, it is raised to the power 4th. Be careful. Number two, it has to be in Kelvin. This is mandatory for this equation. Temperature has to be in Kelvin. This is not delta T, so it's not the same, which means that that cannot be degree C, wrong, because it's not based on delta T, it's based on T only, right? So keep that in mind, and the unit of that temperature has to be in Kelvin. So what about, this is a total energy coming from one surface here. What if this surface is also emitting? By the way, any surface can emit energy at any degree. Your body is emitting energy at any temperature. So now if we put two surfaces next to each other and they are exchanging radiation between each other, how to calculate the Q exchange? Q exchange will be calculated from the same equation. And for sure, the epsilon will be for the more dominant surface area of the more dominant or radiating surface, the one has a higher temperature. Boltzmann curve is not going to change, but now we will have the higher temperature to the fourth, T surface minus to the fourth, minus T surrounding also to the fourth. So this is now is not going to calculate the emitted energy. This will calculate the exchanged energy by radiation between two different surfaces here. Okay, and the same defined here. Surface area Boltzmann constant, emissivity, T surface, it's in Kelvin to the power 4, T surrounding is in Kelvin as well. So T surrounding has to be in Kelvin as well. And don't tell me that this is delta T. This is not delta T. This is T to the fourth minus T to the fourth. So here, that's Kelvin, cannot be the same as delta T degree C. So please keep that in mind as well. Okay. So if I go back to this example, energy will be generated in the fuel rod. Energy will transport from the fuel rod or the fuel pellet all the way to the surface of the fuel pellet. By what? By conduction, because energy is going through a solid material. Now, we have two mechanisms that are occurring simultaneously from the fuel pellet. There is conduction. Heat will be going by conduction through the stagnant helium layer, but also because of that high temperature surface of the fuel, it will start emitting or exchanging energy by radiation to the inner face of that fuel cladding. Now, that inner face of fuel cladding, will receive heat by two mechanisms. He will receive conduction and he will receive by radiation. Now, all this energy will be come together, then they will transport by conduction through the thickness of the wall of the cladding material. Then that total energy will transport into radiation by convection, and go by convection actually to the outside coolant here. So that's basically what I need to share with you about the fundamentals of the mechanisms of heat transfer, including the radiation. So again, the point is you don't have to do this, or you don't have to have these mechanisms happening in a sequence, because they could happen at the same time. As I mentioned, that the heat transport from the fuel pellet to the interface of the cladding could be occurring by multiple mechanisms here. So if I give you a very simple example here, just let me, so let's assume that you have a surface like this or a body like this. And I give you the following information here. That body has a thermal conductivity of 5. That's example here. Then that's 5 watt per meter Kelvin. And this is a kind of plane type or plane surface that's sitting on a side, right? Then there is a source of heating coming from the bottom, for the whole face at the bottom, with a heat flux value equal 5,000. That's a heat flux, so that's watt per meter square. The thickness of this plate is 10 millimeter. The lower face, the whole face at the bottom, is kept at T equal 120 degrees C. Then the top face here has an epsilon of 0.85. unknown top face temperature, but this plate is exposed at the top to H equal 50 watt per meter square Kelvin, and T infinity equal 25 degrees C. In the meantime, this body here is sitting in a room where I was giving the surrounding temperature equal unknown temperature. Now I need to find the T top. I need to find the surrounding temperature. So let's explain the mechanism of energy transport. It's clear. There is a heat of source here, so I'm expecting that lower face here or that lower surface here will have the highest temperature. So heat is coming from a supply source to heat up that lower face to keep it at 120 degrees. Then I'm expecting heat is going to go from the bottom to the top, going through that solid plate, which means that we are dealing with correct conduction. Now the heat will be sitting over the upper face and find a way to leave that face. When it's set over that face, it will find two different ways that may happen, that should happen simultaneously, right? That top face is exposed to, I see T infinity H, that's a property of a fluid, that's fluid temperature, so I have a fluid here. But also, the upper face has an epsilon. It has the ability to radiate energy as well. And we know that energy will be emitted to the surrounding, which has unknown temperatures. So I will have conduction, and then I will have convection to the fluid simultaneously with radiation to the surrounding. So whatever that quantity of energy coming from the bottom face to the top face will move simultaneously by two mechanisms. They don't have to be equally. I didn't say that they get a split, but the total coming from the bottom to the up will be dissipated by two mechanisms at the same time. So if I look to the upper face, whatever is coming in is going to be separated out, right? So I would say in a simple language here, Q conduction should equal the quantity that's going to be removed by convection plus whatever that's going to be moved by radiation. Whatever is coming by conduction from the bottom to the top should be equal the summation of what's going to be removed by convection and radiation at the same time. This is very important equation here. Okay. Then, again, keep in mind that we need to calculate the top surface temperature and the surrounding temperature. Now, let's look to the top surface temperature. Between the bottom and the top, what do we have? We have conduction. What's the equation of the conduction? Q is equal K A TH minus TL divided by the spacing between these two surfaces here. Now, this body here is not vertical. It's laying down to its side. So heat is going that way, right? So this is T hot. The upper face is T low, which is T top. So this will be the 120 degrees C. This will be the T top I'm looking for. And what's the spacing between two faces? It's 10 millimeter, which is going to be 10. I will divide by 1,000, and that's now becoming to be a meter. That's 120 degrees C. So I'm going to get this in degrees C as well. K is given by 5 watt per meter Kelvin. What is the definition of A? A is the area perpendicular to the heat. It's perpendicular to this, right? So it's either the upper face area or the lower face area. But remember, I don't have the value of Q, right? So if I don't have the value of Q, that's going to be two unknowns here, right? But if I divide both sides of the equation by A, what I'm going to get? Q double prime is equal K, which is 5, times 120 minus T top divided by 10 over 1,000, that's 0.01. What's Q double prime? This is the source of heat flux that's coming in. Because whatever is coming in by the external source will be exactly the same one that's going to be conducted up. So this is actually 5,000. So I can say that 5,000 is simply equal to 5 times 120 minus T top divided by 0.01. So that's going to be 50 divided by 5, that's going to be 10. Then T top will be, I'm expecting the top temperature will be lower than this. So it's going to be actually 110 degrees C. That's T top. That's just by using conduction here. Okay, now the same quantity of heat that's coming from the external source going through that by conduction, this is equal quantities, then it will split from that point to the outside. So instead of writing this equation as Q, I will write this equation as Q double prime, right? So what I'm going to do, I'm going to say Q double prime conduction equal to Q double prime convection plus Q double prime radiation. Why I did that? Each one of these three terms here, it has A. A of the conduction is the area perpendicular to the heat transfer, which is this shaded area here. If I look to the convection, it is the surface area that becoming intact with the fluid. That's convection will happen from the upper surface here, so the same area. And radiation will be, energy will be emitted from the same surface area up here. So A is the same for the three terms here. So that's why I divided by the same A. This is the 5,000. That's the heat flux that's supplied is going to go by conduction. What's Q double dash convection? The equation is Q equal H surface area times delta T. That's Q. I will divide by surface area. So Q by surface area. This will be H delta T. So I'm going to have this equal H delta T. Heat is going out. So that's going to be T top minus T infinity plus radiation. Q radiation is equal epsilon sigma A T to the force, T surface to the force minus T surrounding to the force. And that's why I give you that. We need that T surrounding temperature. So I will divide by A both sides here to get the heat flux. Sigma A, sigma epsilon T surface to the force minus T surrounding the force. So this will be the heat flux. So this will be epsilon sigma T surface. It's the surface temperature here, which is T top to the fourth minus T surrounding to the fourth. Okay. H is given, that's 50. T top is 110. We didn't calculate that. T infinity is given by 25. Now, epsilon is given by 0.85. Sigma, Boltzmann, 5.67 times 10 to the minus 8. T top, 110 plus 273. Remember, it's condition for this equation to be in Kelvin. Now, that's the unknown in the equation. So if I write down the equation with all the values I have right now, I'm going to have it that way. I will have 5,000 equal to 50 times 110 minus 25 plus 0.85 times 5.67 times 10 to the minus 8. 110 plus 273 to the fourth minus T surrounding to the fourth. Okay, now this is Kelvin. This is Kelvin. Said, okay, let's make everything in Kelvin. I'm going to add to this 273 minus 25 plus 273. Kelvin will be coming out. So this is going to be Kelvin. So now I have everything is consistent here. So 110 minus 25 multiplied by 50, that's going to be a number. So that's going to be 5,000 minus 50 times 110 minus 25. Then I'm going to divide by this term here, which is 0.85, 5.67 times 10 to the minus 8. Right? This should equal to 110 plus 273. That's going to be 373, 378, 383. Sorry. 273 plus 10, 283 plus 100, 383 to the fourth minus T surrounding to the fourth. So I will bring T surrounding to this side, the fourth equal 383, the fourth minus 5,000 minus 50 times 110 minus 25, that's going to be 85 divided by 0.85 times 5.67 times 10 to the minus 8. Then that's it. Then you can actually get T surrounding out of this equation. And remember, the unit of T surrounding will be in Kelvin. So you can get that value for T surrounding, then you can subtract 273 to get that temperature in degrees C. So this is just an example to combine all the different mechanisms of conduction, convection, radiation. So all mechanisms are included here. And what's more important is to keep in mind that you could have more than one mechanism occurring simultaneously with others. So that's very important. Okay. So I don't know if I have the final number for that. Let me see if I have my calculator and I can calculate that for you guys. I don't recall the final number. I have my calculator here, so let me look to that number. Just when you solve it, you confirm the value here. So 5,000 minus 50 times 85. Then I will divide by 0.85. Then I will divide by 5.67 10 to the minus 8. So this is coming that term here, coming to be 1.56 into the 10. Wow, that's huge. Then I'm going to put that in a negative value. Then plus 383 raised to the exponent of 4. So that difference is coming to be 5.96 times 10 to the 9. Then I will remember this is T to the fourth, right? So I'm going to get T only. So I'm going to get T surface or T surrounding. I'm going to take that to the power of 1/4. So that's going to be exponent to 0.25. So I got that 277.8 Kelvin. Then if I subtract minus 273, forget about the 0.15. It's we know that T Kelvin is 273.15. So we ignore that small fraction. That's going to be 4.8 degrees C. So the surrounding temperature is basically about 5 degrees C, which makes sense to have everything that's surrounding this surface to be colder, right? So we're coming from 120, 110 at the top, surrounded by a fluid at 25, and the surrounding here is 5 degrees C. And that should make sense from the perspectives of the numbers here. So that's will conclude the mechanisms of heat transfer, conduction, convection, radiation, with an example how to use this formula to do an example, combine the example here. So that's conclude that part. So before we leave this exercise that's showing the different mechanisms of heat transfer that combine conduction, convection, and radiation together, I would like to explain one concept that's very important here. So let's recap that exercise here. So we had that body that was receiving a heat flux from the bottom, right? And what I'm going to do, I'm going to call that energy. Energy N. Then what happened? Energy conducted through the body, right? Then as soon as that energy reached the surface, that energy got removed by two different mechanisms, right? So that's by convection, and this by radiation. And the transport was by conduction, and there was energy N here. So if I draw, if I take a border surrounding this body, and I decided to take that free body diagram of this solid surface, then I will try to draw not the force distribution over this body here, but I will do the energy distribution. So we will find that we have two distinguished energy here. We have energy in, and we also have energy out. I'm gonna call that E out, okay? I understand that energy out has happened by two different mechanisms, right? But at the end, the total energy that went out by convection and radiation together, I can add up these two quantities and I call them the energy out, okay? So we have energy in and energy out. That's for this case. Now, let me assume that we have the same body. Before I draw that body here. And in this case, if you recall the example, we assume that the energy supplied by the heat flux that was coming in, it is the same quantity that went through the body by conduction. And then it's actually divided, not equally, into the radiation convection. So I would easily write down for this equation here that the energy in was actually equal to the energy out, correct? And that's simply the energy balance for this case here. Now, let's assume we have the same body. We have a source of energy in. Then energy will be removed by whatever the number of mechanisms that we have. So that's energy out. But in the same times, I'm going to imagine that inside this body here, I'm having chemicals that they are reacting and produce energy. Or I have an electric wire that's sitting inside that body connected to an electric source. So this wire will produce energy as well. This kind of energy generated inside the body, we call that energy generated. Okay? So what's going to happen here? It's going to happen that I have energy coming in. There is a source that's adding energy generated inside the body. And the combination between the En and E generated will equally, the adds up of these two quantities will removed outside by E out. So if I want to write the energy equation for this situation here, I would simply say that the summation of the energy in plus the energy generated, both will actually leave out. What I'm saying here is true under one circumstance or one condition. What do we call that condition? If the total energy in equal the total energy out, we call that steady state situation. Steady state condition. As long as the quantity coming in equal the quantity leaving out, that's a steady state condition. So I can say here that I have a steady state condition as well. So under steady state conditions or condition, the total energy in equal the total energy out. For this case here, the total energy in plus the total energy generated inside the body should equal to the total energy that's going out from that body. Okay? So that's the energy balance for this case. What if the steady state condition is not satisfied? If the steady state condition is not satisfied, the inlet and the outlet will not be equal. So there will be maybe more energy in than the energy out. So where is that difference is going to go? It's going to be stored inside that body. Okay? Maybe the summation of the energy in and the energy generated is not equal. It's much more than the energy going out. Where is that difference going to go? It's going to be stored there. So when you break down the steady state condition, you go under unsteady condition. Now we're going to see a new term to show up called stored energy. which if I draw down again the free body diagram, I may have a source of energy that's coming in, En. Then I will have internally generating Eg. Then there is E out. But because I'm going under unsteady condition, the summation of the in and generated is not going to equal the out. So I would have a value for Es. So the energy stored is going to be called E subscript S. So in this situation, how to get the relationship between these two? So in a simple language, whatever is in plus whatever is generated should be balanced by the energy out plus the energy stored. These are in, these are supplying energy to the body. These are either storing or ejecting energy from the body. So the energy balance equation will be written in that form. Usually, since we are talking about unsteady, let me recap first what's the exact definition of the word steady. The word steady in any process means that there is no change relative to the time. So the word steady here means no change with time. So when I say unsteady, this means that whatever you are talking about, energy, pressure, temperature, anything that change as a function of time, it's called unsteady conditions. So this means that change with time. So the time is already exist in the problem, which means that in reality, we know that energy, what's the unit of energy? It's usually joule, right? Or kilojoule or megajoule or whatever. But because we have time in the situation, you will always find that the E has a dot at the top. And the dot here means the rate. That's a time presentation in the equation. So the rate of energy supplied plus the rate of energy generated equal the rate of energy out plus the rate of the energy stored. And this equation now, it's called the energy balance equation. And this is more the general form here. So let's assume that we don't have that E generated term. It will take us to the case of En equal E out plus E steady. But if I have no heat generation and steady, these two terms will go away. So under a steady state condition, this will be 0. This will equal 0 under steady condition, steady state condition. Then if there is no heat generation, it will take us to this case here. If there is heat generation, it will take us to this case here. So this is a more generalized form of the equation. Okay, so if we under steady state, this is like special cases here. Steady state, the equation will be E dot N plus E dot generated equal E dot out. And if you add to the steady state that there is no heat generation, which is generated internally, this means that E generation will goes away and the equation will be E dot in should equal to E dot out. So I can derive these two special cases here, this one and this one, from the more generalized equation you can see here. Okay, so this is very important to understand. There is a big energy balance equation that we can use because we're gonna need that all the time. Again, and energy is conserved, right? Energy conservation concept has to be applied. Energy cannot be created from nothing, but it can just change from one form to the other, right? Or can create it from nothing or can be disappeared. It has to convert from one form to the other. And that's the concept of conservation of energy. So keep that in mind all the time. And you should be aware of this equation here. Okay. Let me look more, provide some details about this equation. Let me write down the equation again. So the equation is energy dot in plus energy dot generated equal energy dot out plus energy dot stored. So the energy dot in or energy dot out would be actually done by any of the mechanisms of heat transfer. So they could be supplied by convection and rejected by convection, or supplied by convection and rejected by convection and radiation. Very similar to what we did in the example. So these are the energy in and energy out. And again, the unit would be actually in watts, right? That's one thing. Do you recall at the beginning when we, at the beginning of that set of lecture, we were talking about the quantities of heat transfer, and we defined Q, Q prime, Q double prime, and Q triple prime, or Q dot. And we defined that Q dot is simply the volumetric heat generation. If you recall the units, it was actually watt per meter cube. Now we are hearing a new term here called E dot generated or generation. And we know that the unit, this is the heat generation, and has a unit of watts. Can we drive a relationship between this E dot capital and Q dot? It's clear. If I multiply Q dot times the volume, I should get that. So this is very important equation here. The total energy generated, or the rate of energy generated within a body, it's equal to the volumetric heat generation times the volume of the body. We can call the volume V, or we can call it actually V dash, either one. But I can write down the equation. E dot generated is simply equal to the volumetric heat generation, Q dot or Q triple prime, times the volume of the body. And this is a very important equation that we're going to need a lot. So this is a general energy balance equation. And this is another equation that we may use. We will use, not may, we will use it a lot in the along the course. The new term that we just got here is the energy stored, E dot stored. Let's recall your middle school, high school equation for calculating the heat stored by a body. Very simple. You remember, guys, the equation, it's mc delta T, right? What is M is the mass of the body. That's kilogram. C is the specific heat. And it has a unit of joule or kilojoule per kilogram Kelvin. It depends on the given information. And delta T is the temperature difference. Which has a unit of either Kelvin or degree C. So I can write down the unit of C is joule per kilogram degree C. It doesn't matter because it's based on delta T, and delta T could be either by Kelvin or degree C. But if you look to the overall unit here, that's kilogram. That's joule per kilogram Kelvin. That's Kelvin. Kelvin will go away here. Kilogram will go away. So joule is going to be the final unit. But we said this has to be consistent with the other. So it has to be in watts. So I had to divide that joule per time. So I'm going to divide that equation per time to make adjustment for the unit. And the time that we're going to divide by is actually delta T. So delta T is the time. So let's, and that should be in seconds. Let's write down this equation in more scientific format. So the energy dot stored should equal to M times C times dt by d time t. And we call that dt by d time t is the temperature gradient. Temperature time gradient. Okay? So that's the final equation that we use to calculate actually the energy stored. So when we have a steady state, you guys recall what's the definition of steady state? Nothing changed relative to time. So d of anything relative to the time is equal 0, which means that under a steady state, the energy stored should equal 0. And that's why this term is not showing up in this case or this case, because this is steady state condition. This is also steady state condition. Under steady state condition, nothing changed relative to the time. So the derivative here, dt by dt, will goes away, and that's make the energy stored to goes away as well. Okay. So that's very important here. In some cases, I'm going to frame that equation here because that's how we calculate the energy stored. In some other references actually, or other books actually, you will see that mass is replaced by something else. We know that density is simply equal to the mass over the volume. Write it down V or write it down V bar, whatever you like it. So I can actually density take the symbol rho. So I can replace mass with rho times V. So sometimes you see this equation, E dot stored, it's equal to rho, which is the density of the material, times V, which is a volume, times dt, times C, times dt by d times t. This is just a different form of the energy stored equation that you may see down the course, or you can see it actually with in other references. It used a lot. So that's the outtake from the example that we covered. We were able to drive, number one, energy balance equation. We defined the energy generated, total energy generated within a body. We defined what steady and unsteady situation here, and we did learn how to calculate the energy stored in this case when you have unsteady condition here. So this is very important. From that energy balance equation, we can drive anything. So we will move forward on a different way of analyzing the mechanisms of heat transfer. So we have three equations. We got Fourier's law for conduction, we got the Newton's law of cooling for the convection, and we got the radiation heat transfer Stephen-Boltzmann equation. We will not focus on radiation. As I mentioned before, it's beyond the limits of or the capacity of that course. But we will learn how to do the conduction and convection in a different way, in a simpler way, which will help a lot when we come to the thermal transport analysis of nuclear fuel of different shapes. So I'm taking you step by step gradually to understand the best way to do the analysis for nuclear fuel heat transport. So stick with me with the upcoming session, and we're going to talk about this. And that's conclude that part of the class.